Off air.
Oh, we're live.
We're
Oh,
live.
we are?
We're
Yep.
live. Hey, we're live. We're live. I think we mentioned
Oh,
some place.
so we are. Okay.
Okay,
Yeah,
everybody.
we are. Hey,
Um,
that's working. Okay.
we, discipline, kids. Discipline, discipline. Since we're live,
So we are. Okay. Hey, that's working. Okay.
could everybody please mute themselves? Okay, muted. Okay. Hi, everybody. As you can see, we've been having problems with getting and we've got feedback coming. Technical difficulties. Give me a minute here while I straighten them out again, folks. And we've got feedback coming.
I think that's coming
Do
on
we
your
still
end
have
because
feedback coming? Okay, it sounds like we've
no, we're
gotten
good.
rid of that feedback. I don't, however, know that we're live. Tolga, I think just shake your head up and down if we're live.
We are.
We've been having some technical difficulties today because again we're trying new things and we got part of it all worked out, but another part of it isn't worked out. Namely, TJ, the presenter, seems to be having audio difficulties and he can't hear us. Now he can still give the program, but he signed his computer out and he's signing back in, trying to get in. So it may take us a few minutes before we get back to the heart of the story with him. So let us go to the prepared presentation for today. And as you can see, we're on the Astro Imaging channel. And this is the page that you usually see. And we've got a number of things we want to show you about. On November 11th, I think it is, Mercury is going to pass right in front of the sun. And if you're bright and courageous, you can wake up in the morning and you can go out and see it. For those of you on the East Coast, you'll be able to see the entire transit. And for those of us out here on the West Coast, we're going to see, if we get up early enough, we'll see it coming up at sunrise so we can start taking pictures of it then. But the transit of Mercury has been a very important thing through the years because it allowed us to judge how big the Earth is or how big the solar system is. And that was something we didn't know until it's transit of Mercury is where it really started happening. And they got into it. Oh, you know what? I'm not sharing my screen again. Hang on for a second here. Okay, now I'm sharing my screen again. Go back to the PowerPoint. And now we should be seeing everything properly. If we're in the right place, Eastern United States will do, and South America, obviously, you'll see the whole transit. Out here in the West, we'll only see it coming up at sunrise, and we probably won't see very much of it at all coming from California. I've seen two or three Mercury transits, and I've seen both of the Venus transits, one of which I was with Fred Espenek. He's Mr. Eclipse, but his time working for NASA, he made all these programs up so that we could all see what the world was like during transits and eclipses and things. Anyway, that's what we're going to talk about tonight, how to get ready for that. I want to remind you that there are various things you can see. You can see by going down here, you can click and you can watch the program. And if you click down here in the corner, you see this little green and white area, you can get to Rumble Talk. And on Rumble Talk, you can make comments as to what's happening during the show. But I've got to tell you that we have largely been migrating from Rumble Talk over to YouTube comments itself. And in YouTube comments, you can see that you can actually make comments and various other things that are really important to us. The comments are really important because in YouTube, they stay with the program through the years. And so if you want to see what the comments, the questions were, the arguments about how people were seeing things, you can kind of follow along. We don't have that advantage with Rumble Talk, so it's a nice thing to come over here. Some of the other things you'll notice if you go over to the YouTube, you can make donations, you know, and we would do appreciate the donations. They help run the program. It costs some money to rent the programs that we use to keep everything going and all that other stuff. So we appreciate it if you could do something to get us going there. And but mostly if you could subscribe too. You see, for certain levels of subscription to YouTube, the Astro Imaging channel can take advantage of other levels of support from YouTube. And we're at about 7,400 now, and we're continuing to grow slowly. If we could make it to 10,000, it would be good. So go ahead and subscribe to the channel. It would help us. Taking a preview of some of the things coming up in the future. TJ is going to be today, and then we're going to have some other people. Richard Wright will be here in a couple of weeks. Richard is a friend of the family here. He's been on the show before, and he'll be on again in the future. He also just committed to doing Nightfall. I think some of you people have seen the program we did on Nightfall, you know, imaging rigs of Nightfall, and I think they're still on they're certainly still on the Astro Imaging channel, so you can get an idea of what it is. But it's really a lot of fun. And Richard Wright's going to be doing Nightfall. That's in October, so hope you can come for that. And I think that we've got Tim checking in. That's that noise that I'm hearing in the background, or maybe that's my phone going off. At any rate, so you can see we've got a whole lot of things planned. August workshop, if you go to this part of the website right here where it says workshop, you can call up the workshop, and we've got some data there, and there's an interesting thing going on with the data. We've got about, I think, 8 people have put things into the put things in so far so that we can see what's happening in the workshop, and that's pretty cool. And we've got some new people, so I'm looking forward to hearing from the new people that we haven't heard process before. We got some of the returnees coming in. This is fairly easy to process data. It's not as clean as it was from Terry or Eric before, but I think you might enjoy it. So please take your shot at that and get it submitted. We'd like it submitted by next week or the week after that, so we can start inviting you into the house here. So please do that. We're going to start inviting people next week sometime. Now, remember, if you post here, you post an offering, it may be a day or two before I get around to approving them, okay? But at any rate, we're here to talk about the transit of Mercury coming up. And Tim, are you still on my phone? Okay. And do we have the phone problem still?
I'm here.
Okay.
Can you hear me?
I can hear you live, but I can also hear you over the phone. So what's happening?
Okay, I can take you off speakerphone and get going if you want.
Yeah, go ahead. Take me off speakerphone, share your screen, and do your presentation.
Okay.
Are you speaking, Tim?
All right, so do you have the slideshow up? Can you see that?
Yes. Yes, you're good.
Yeah, we see it.
Okay. So sorry about the delay there. Tonight we're going to be talking about preparing for and imaging the 2019 Mercury solar transit. I just want to make sure that everyone sees the slideshow and sees that it all looks good. Am I all set to go?
Yes, you are. Can you hear
Looks
us,
good.
Tim?
Okay.
Can you hear us?
I think he can hear me, but not you.
Okay.
Is that right, Tim? Can you hear me?
Okay, so tonight we're going to talk about
Maybe
solar safety. I emphasize safety, because it's so easy to make a mistake in this, and one mistake can screw up your eyes, screw up your camera gear, screw up your telescope, everything that can go wrong with this. So I'm just going to emphasize safety throughout the presentation. We're going to talk about what is the solar transit, We're going to talk about the November 2019 Mercury solar transit, the focal lengths, tripods, solar imaging cameras, solar filters, the different types of solar dedicated scopes, the features on the sun that we can image, and I'll also get into a little bit of stacking, sharpening, and processing towards the end. A little bit about myself. I live in Katie'ville, New York. It's upstate New York, just south of Montreal. It's right on Lake Champlain. I've been astroimaging since 2013, and I'm also a member of the Adirondack Sky Center's advisory board, and I regularly instruct and present at the Sky Center's imaging conference every fall, and I give presentations, and I do a lot of outreach events throughout the year. So that's a little bit about me. My normal setup for outreach is a Lunt 152 double stack scope with a 80 millimeter Lunt engineering refractor side by side, and I broadcast a live image of the sun in calcium K light. And if you don't know what calcium K light is, we'll get into that during the presentation. So first, what is a solar transit? The solar transit's when an object gets between the Earth and the sun, and it appears against the background of the sun. So we have the Mercury transit, we have the Venus transit back in June 2012. And unfortunately, the next Venus transit isn't going to be until December 2117. I wish I would be around for that, but I know I won't be. You can also capture International Space Station transit, satellites, the moon for solar eclipses, birds, and airplanes. I actually just saw a really cool F-18 transit of the sun, which was really neat. The ISS transit that you see in the presentation right now, that's going to be larger than what we're going to see Mercury, and I'll get into the sizes during the presentation. So the Mercury solar transit, it's going to be November 11th, 2019. Unfortunately, not all of the world is going to see the transit. And you can see the eastern coast and South America is going to see the entire transit as long as you have clear skies. Over Africa and Europe, you're going to have the partial transit visible at sunset. And then on the west coast, the northern Mexico area, you're going to have the partial transit at sunrise. So November 11, 2019, it's going to start at about 12:35 UTC time or 7:35 a.m. Eastern time, my time. The greatest transit is going to be at 15:19, so about 10:19 a.m. Eastern time, and it's going to end at 18:04 UTC time, about 1:04 p.m. Eastern time, my time. And the Mercury solar transit, the apparent size of the sun is 32.3 arc minutes. When we look at Mercury, it's only going to be about 10 arc seconds, which is going to be extremely small. And you can see this diagram I pulled off my Sky Safari app. There's different size types of framing you can do, and I'm going to talk a little bit about the framing during the presentation. The last Mercury transit was back on May 9th, 2016, and we're not going to see another Mercury transit after this one until November 13th, 2032. So quite some time. And just a little to add something, there's about 13 Mercury transit every 100 years. So this is a rare event that we're going to be seeing this November 11th, as long as we have clear skies for it. And we have to start somewhere, and that's why practice, practice, practice. You want to get out there with your solar scopes or with your white light filters and start imaging ahead of time, because you can see, as you can see from the screen, my first solar images back in May 2nd, 2013, when I was using my 450D DSLR hooked up to my Coronado PST, it wasn't that impressive. You can see a couple prominences on the limb, the limb of the sun, and you can also see a filament and a couple small sunspots on the disk. And again, I'm going to talk a little bit about safety. You can see this is a cap that I actually fried on accident. So no matter if you're a pro out there doing it every day, mistakes happen, and you just have to take that extra precaution to make sure that you're properly filtered. So when I set up my solar scope, I'm not going to look through that scope unless I triple check my scope, make sure all the filters are in place and all the thumb screws are locked. So you never, ever, ever want to look or image the sun without a proper solar filter. You can damage your eyes, your camera, your equipment, and also property. You can start fires if you're imaging or if you're looking through your solar scope around dry leaves or dry vegetation. You always want to inspect your filters for holes and tears. And when you set up, you want to make sure your finder scopes are covered with a lens cap or a solar filter if you're using that finder scope. And also research and double check your setup to make sure it is safe. Again, I'm going to get into a lot about solar scopes, but you always want to research and make sure, double check, triple check your equipment to make sure you're safe and good to go. And when we start out, you have your tripods and mounts. The Earth rotates 360 degrees every 24 hours, which means the sun drifts quite a bit. It actually drifts its own diameter every 2 minutes. Fixed tripods, like for your DSLR camera, those work great for the full disc solar images. But when you're zooming in on that sunspot or the Mercury transit, you got to remember it's not going to track, so you're going to get a little bit of drift across the screen. So that's why I like to use motorized mounts. I use in the image on the screen, you can see I'm using a Celestron AVX. I love my AVX mount for the solar work because it's small, light. I can carry it anywhere. If it starts to rain, I can just pick it up and drag it in. Whereas my Lunt 152, I have to set it up on my CGEM DX mount, which I can't do that. So if it starts to rain or storms come, I have to throw my TeleGizMOS cover over it. When you're aligning with a motorized mount, you want to make sure you're polar aligned. This will help the drift. And what I use is I use a simple compass, and I know my magnetic declination is -15 degrees here. And you can look up your magnetic declination at magnetic-declination.com. So there's a little map on the upper right. It shows the declination lines, and it'll tell you if you're westerly deviation or eastern deviation. So when I'm setting up my mount, I always want to offset for that with my polar. And because the sun's such a large target, you don't have to be that precise with your compass. However, if you want to get precise, it's very simple to drift align your mount, whereas you just use the altitude and azimuth knobs to just kind of center the sun. And eventually the sun's going to be tracking normal. There's also the solar tracking option in the mount that you may want to activate. I don't activate the solar tracking feature in my mount. I just use the normal tracking on it. And here's the magnetic north you can see on the left, and then polar north on the right. And you can see how much of a difference it makes for me. So just because I bring my compass out, I don't want to set my mount due north. I want to offset it for the polar north so I can track the sun. And another solution, which I just picked up at NEAF this year, and I love it, I've had it out several times, is this AstroHuTech Hinode's solar guider. It keeps me locked on the sun all day. And during my outreach events, it's one less thing I have to keep track of while I talk to everyone about the sun and show the sun off. And even if a kid yanks on the eyepiece a little bit, the scope will stay on the sun and center it. It's basically a solar guider for the sun, and it works very well. I highly recommend it if you really want to get into some solar imaging, some serious solar imaging. Another thing you want to do while you're out there imaging the sun, you have the sun's glare. You really don't think about it until you get out there. So you can see during my outreach events, I have a simple cardboard box that I sewed some fabric for, and I just made it look kind of nice. But I mean, if you take the fabric off, it's just cardboard box. But it helps get rid of the glare so everybody can see the sun without looking at a screen that's completely white or glared over from the sun. If I'm out there by myself, I use AstroHuTech, or actually, I'm sorry, a TeleGizMOS solar cover, and I basically use it as a tent. I've seen some ice fishing clamshells that have been used, and those are great too. But it's very simple, and you can even use a towel if you want to eliminate the glare without getting too creative. And again, the scale of the sun's going to be about 32.3 arc minutes, and Mercury is going to be about 10 arc seconds. And when you hold your pinky up to the sky, your pinky is about 1 degree. So the sun's apparent size when you're looking at in the sky is only about half the width of your pinky finger. So that just puts it into perspective. And then Mercury at 10 arc seconds, it's going to be extremely small. There's going to be, I mean, we're in solar minimum right now, but there may be some sunspots on the sun come November that are larger than Mercury. And then this is one of the most trickiest parts of imaging the sun when you're set up and going is finding the sun, especially when you're using a high focal length scope. I've used my Daystar Quark pushing f30, and it's almost impossible to find the sun without the Soul Searcher, TeleVue Soul Searcher, or using the Daystar Solar Bullet. I really recommend the TeleVue Soul Searcher. It's a great feature, and it basically projects the sunlight on a screen, and you can adjust it, you can calibrate it so it's centered. So when I look for the sun, I know exactly where it has to be on that little white screen. And then the focal length. This is very basic. I'm sure everybody knows about focal length, but we're going to get into a little bit of focal length. So I want to make sure everybody's clear on that. And focal length's the distance between the center of a convex lens or a concave mirror. In my instance, I always use refractors. I don't use my SCT scope for solar imaging, and I don't use my Newtonian for solar imaging. Even though I have solar filters for it, I like to use my refractors. And the focal point is the point where the light meet and converge on. And here you can see, this is a simple diagram I made off Sky Safari app. I love my Sky Safari app because you can put any telescope in and your camera, your sensor size, and you can see ahead of time and plan the size, what you're going to image. So on the left, you can see I have my Lunt 80 millimeter refractor, and it's about 525 millimeters focal length, and I'm using a ZWO 174 camera. And then on the right, it's the 9 1/4 SCT, which has a 2,350 millimeter focal length with the same camera. You can see how that field of view is going to be different. So you want to get out there and practice and plan how you're going to image the sun. When I do transits, I like to use my Lunt 80 millimeter, which has a perfect full disc setup with my ASI 174 camera. And I like to get a series of images of the transit going across the disk of the sun. And the camera sensor size, depending on what your goals are, again, it's very critical to match your sensor size up with the focal length. And if you're using a larger sensor like a DSLR, a full frame, or the APS-C, you're with a shorter focal length lens, you're going to be limited to the full disk image of the sun. And unless you're using like a Quark, the Quark adapter for the DSLR, then you'll be able to get some really nice images. But you can see on the image on the right with my DSLR, I have a 300 millimeter zoom lens, and I just have a simple little Daystar white light filter. It's just a cardboard filter that goes over the lens, and it's nice and tight, so I don't have to worry about the wind blowing it off. But again, I always double check and make sure that white light filter is in place because I don't want to fry my camera with the sun and the 300 millimeter zoom lens. And this is a little diagram I used when I first started imaging. I started with my DSLR, my 450D, and then I went to the point gray Chameleon and then the ASI 174. So you can see the difference in the sensor sizes. And on the left-hand side of the presentation, again, there's a Sky Safari diagram I created with the different size camera sensors on the Lunt 152 scope. So you can see the Lunt 152 scope, depending on the camera you're using, the frame rate's going to be different. You're also going to have a different field of view. So you can see the zoomed in view is the ASI 178. The middle view is the ASI 174, which I don't like that camera with the for solar work because I like to get a nice full disc. So that's where I'll use my ASI 1600 mm Pro. And it just because it's the 1600 mm Pro, it's a slower frame rate than the higher speed 174 or the 178, but still it catches high resolution images for a full disc image of the sun. And here's a couple different sizes just to show you the difference. You have the full frame sensor, which is about 24 by 36 millimeters. And then you work your way down to the consumer DSLRs, which are smaller, less expensive. And they're nice cameras to travel. And you can also use them for terrestrial photography as well. Then you get down to ZWO. I like using the ZWO cameras for my solar and planetary work. And another thing I wanted to mention, because I brought up the ASI 1600, they make the ASI 1600 cooled and uncooled. They also make the 174 camera cooled and uncooled. You do not need a cooled camera for solar work because our exposure's so quick and so fast that you don't get the noise like you would for long exposures like night imaging. So people think that just because they see a cooled camera, they think, oh, I need that cooled camera for my solar imaging. It's going to cool it with the sun, but that's not true because you have the solar filters in place. So it's not like your camera is going to overheat, and it's just an extra expense if you get the cooled version. But I would recommend getting the cooled version if you want to use it for nighttime photography as well. I love my 1600 mm all around for nighttime and solar work. And you can see the Point Grey Research camera, which is a USB 2 camera. It's not as fast, but it's only $375, and it has a 8.47 by 8.47 square sensor, which I really enjoyed, and I had a great time using it with my first Coronado PST solar scope. And when we're looking at focal lengths to image the sun, based on the size of the sun and the sensor size, for full frames, I would recommend a minimum for full disk imaging, 634 millimeters with a maximum of 1268 millimeters. And this will make sure that you have the full sun and it's not zoomed out enough where you have to really zoom in and the details of the sun, sunspots, and Mercury is distorted. However, if you go up to the 1268, you're going to be zoomed in quite a bit on the solar disk, but that 1268 millimeter focal length is going to be nice, fits the whole sun in your image. And then the Nikon, same thing. It's a APS-C, so it's Nikon and Canon. They're both around the same, 415 millimeter minimum for the Nikon, and Canon 391 millimeter. So if you're traveling too for the Mercury transit, this may be easier for you to fit a smaller scope in your bag if you want to get that full disc sun. So then the full frame cameras are nice because they're faster, they're higher quality, and they don't skip frames. But the Canon and the Nikon, they are reliable and they're good cameras to use as well. And you hear about pixel size and sampling with nighttime photography. Daytime, for the solar work that we do, it's very important not to be undersampled. So I have a formula that I use, and I see formulas all over the place, but this is the one that I personally use. Focal ratio divided by 5 is the approximate camera pixel size. And I've seen people use 2.4, focal ratio divided by 2.4, but I like the focal ratio divided by 5 because it also will take in effect the seeing, and also it's a little bit more forgiving. Because with solar work, it's better to be oversampled than it is undersampled. So you don't have to worry about that with solar imaging as much as you do for nighttime, because for nighttime photography, if you're oversampled, it means that the light is spread over more pixels and then needed to achieve the full resolution. So you have to have longer exposures. Whereas the daytime, the solar imaging, your exposure is so short, it doesn't matter. It doesn't make a difference. So here's a formula. This is my Lunt 60 millimeter scope with f8.3. So I take that 8.3 divided by 5, and I'm at 1.66. So this tells me that the camera that I'm going to be using should be at least 1.66 microns, which is just about every camera that's out there for the ZWO line. And then you're going to see with the 152 millimeter, which I love this combination. I use my Lunt 152 with the Daystar Quark, which has a built-in Barlow of 4.2x. So when you run that 5.9 times 4.2, you get 24.78, and then 24.78 divided by 5, because that's my pixel size ratio, and I get 4.956. So I want my optimal pixel size of the camera at least 4.956 microns, which is where my ZWO ASI 174 camera comes in. And that's why I love these ZWO ASI 174 for all around solar work. And then when you're imaging monochrome versus color, you'll hear a lot of solar imagers tell you, oh, go with monochrome because it gets more detail. And that's absolutely correct. Because when you have the RGB, a color OSC camera, you have the RGB Bayer matrix, which collects the photons specific to that filter. So there's going to be photons that are rejected, and you're going to lose detail. However, if you're forced to use a DSLR camera, I always tell people to extract the red channel, because that's where most of your data is going to be when you image the sun. So I get rid of the green and the blue channels, and then I process just the red channel, and you still get great results that way. It's not as good as a monochrome camera, but still it still is usable and doable, and I like the results with it. And when you're using DSLRs, you have the ISO settings, and that just determines how sensitive the sensor is to light. It's kind of comparable to the gain with your cameras, but it's different. And the greater the ISO, the brighter your image is going to be. So for my Canon 450D, I always use the ISO 200, and you can see the recommended ISO speeds for f3 to f5.6. You're going to want about an ISO speed of 100, f5.6 to f11, 200, and then f11 or above, ISO 400. And that's because when you're working at f11 or greater, the image is already going to be pretty dim. So you want the ISO to kind of brighten up your image for you, and you get a nice result without all the noise in the background. Shutter speed is the length the image is exposed. So if you're using 1/2000th of a shutter speed, you're not going to let a lot of light in, so your solar disk image is going to be very dim. Whereas if you're using a 3-second shutter exposure, that's obviously too quick, too fast, and these shutters, your image is going to be overexposed, and it's just going to be burnt out, and you're not going to get any details on the solar disk. And you can see I used my DSLR, my 450D, and I took various exposed images with ISO 200, and you can see 1/30th of a second, you can see it's burnt out, whereas 1/2000th of a second, it's too dim. So my happy medium, the image that I like, is the 1/125th of a second. And you can see it's not overexposed and it's not underexposed, and it gives you some flexibility to deal with processing. You can also use a basic fixed tripod with your DSLR and use an intervalometer with your white light filter. This is very inexpensive, and it works. It's a great setup for full disc imaging with a 300mm zoom lens, or you can use the white light filter on the front, and it's basically the intervalometer lets you have hands off your camera. So when you trigger the capture, you're not shaking your DSLR camera, you're not making any vibrations, and you have full control over it. There's also specialized scripted software such as Eclipse Orchestrator or Backyard EOS. When I started off, I used Backyard EOS. Once when the Eclipse came around, I was playing around with Eclipse Orchestrator, which was a lot of fun because you set your script, and Backyard EOS also has a script that you can set too, but Eclipse Orchestrator is geared for like the solar eclipse. So again, this will allow hands-off capture so you don't shake your camera or the image. Unlike DSLR cameras, high-speed CCD/CMOS cameras must be used with a laptop, or now they have the Raspberry Pi USB 3 devices, or the Primalucy Lab, the Eagle, which I've seen some people doing some great solar imaging. Gary Palmer's been using the Primalucy Lab, and that's basically a small computer that he's running remotely to his other computer, and it works. And you're not out there in the sun, but you must use like a motorized focus for it as well. And the Lunt scopes, they actually make a pressure tuner that's remote controlled as well, which I'll talk a little bit about that once we get to the hydrogen alpha scopes. So instead of the ISO, you have the gain, and the gain on the high-speed CCD CMOS cameras basically just amplifies the signal, which increases or decreases the brightness depending on how you play around with that. And again, cooling doesn't matter with your high-speed cameras. You don't need to get one of the cooled cameras, but if you're going to look to use it for nighttime imaging, I highly recommend the cooled camera as well. Another benefit of the high-speed CCD camera as opposed to the DSLR, you're able to freeze the seeing. And I have a clip that I'm going to show you where you can see the seeings jumping around. So you want to capture as much detail as possible in the shortest amount of time. And here's the first camera second camera that I started out with is a point gray Chameleon. You can see it was USB 2, so it was 18 frames per second and 1.3 megapixels. Well, the 174 that I currently use it's a monochrome camera, and it's 128 frames per second at full resolution. But I like to zoom in on my region of interest, which basically in fire capture, you can crop your image and it will increase your frame rate. So if you crop your image down to 640 by 480, then you're working with a maximum of 397 frames per second, and it's a 2.3 megapixel camera. Excuse me. And then file format, you'll see people capture in JPEG or RAW. I always capture 14-bit bit format, and when you're using fire capture or whatever capture software you're using, you'll see settings where you can either set it for 8-bit file format or 16-bit file format, depending on the camera you're using. So if I set it for 16-bit, my camera is a 12-bit camera, it's going to be using 12-bit format. And you can see on the presentation, when you're using 8-bit JPEG, the brightness range for your grays is 0 to 255, whereas when you're using 12 or 14, look at 14-bit format. You have a brightness range of 0 to 16,383, which is going to give you a lot more values to play with your grays at the end when you're processing your image. And if you're using a DSLR, you're going to want to make sure you have a large enough memory card to allow for the storage of your images if you're out there all day imaging. Another option, and it's a cheap way or inexpensive way to image the sun, is with a cell phone camera. Celestron makes a great, it's the NextYZ adapter. I bought it 2 NEFs ago, and I use that for solar imaging. So I let the kids hook up their cameras to my scope, and they have a great time imaging the sun. And as long as you're using a proper filtered scope, you can basically adjust with some of these new apps. You can adjust the exposure. You can play around with it to get a very decent image. And you can see here, there's a nice prominence on the limb of the sun. And if I was to process this a little bit more and put a mask on the outer limb, I could bring out some of the nice little details. But because, like I said earlier, this is a color camera, so it's going to appear more red. So what I would want to do is extract that red channel and process it in monochrome, and then apply false color during post-processing. And then with focus, this is another critical step. When you're focusing with your DSLR, you want to make sure that all your settings are in manual. You don't want to use the autofocus setting because it's going to screw up the disc. And what I do is I zoom into the limb of the disc, or I zoom into a sunspot. But right now with solar minimum, it's very rare to see a sunspot right now. There are a few that pass here or there, but I'll zoom right into the limb, and I'll make sure that limb is as crisp as I can and with a steady hand with my Canon lens. And this is where the motorized focusers come into play, because you're not shaking the scope. It's a lot more effective to get that critical focus. And I have a nice touch that I do where I roll the focus. I find it that happy medium, and I roll it in, roll it out, and then I go back to the middle, and that's usually the critical focus for my high resolution solar imaging when I'm not using the motorized focuser. And so some lenses, so you can see on the left, this is a white light filter that I built for the Lunt Engineering 80mm refractor. And you can see I have my Canon DSLR with a T adapter on it, and I can get a nice full disc image of the sun this way. On the right hand side, you can see I have the Lunt 80mm with the Daystar Quark Hydrogen Alpha eyepiece filter with the ZWO ASI 174 camera. And I also have the, because you have to remember the Daystar Quark has a 4.2x Barlow filter in it. So you're not going to get the full disc image like you would with the Lunt 60mm. So that's why I run them side by side. So I can do the high resolution imaging, and then I can swap it pretty quick over to the Lunt 60. And you can see it's double stacked too, which we'll talk about. And I can get a nice full disc image of the sun. And with the solar filters, we're basically looking at narrow band wavelengths. So on the left, you can see the calcium K, which is my favorite band to image in when I'm looking for transits or the eclipse, or when I'm looking at active sunspots. I love calcium K. There's also calcium H, magnesium, the solar continuum, which is a wider range for white light. And Daystar is making a great sodium filter. It's a sodium eyepiece filter. It's sodium quark. And they also have the hydrogen alpha Daystar quark, and also Lunt has their hydrogen alpha, and Coronado Mead have their hydrogen alpha filters as well. And you can see the wavelengths there. Calcium K, I love calcium K, and I run that on my outreach just because it's on the lower end of the UV wavelength. So a lot of people cannot see calcium K, whereas calcium H is slightly higher at 396 nanometers, and it's a little bit more appeasing to the eyes. So it's easier to see if you're more of a visual imager. Then you have the magnesium made by Daystar, the Daystar magnesium quark, which is 517, and then the solar continuum of 540 nanometers, and sodium and hydrogen alpha. And depending on what you're looking to image on the sun, you can see different features. So whereas the white light filter, you're going to get the wide range of light. So you're looking at the photosphere, you'll see the granules and sunspots. With the white light filter, I like to throw a solar continuum filter on, and I'll talk about that shortly when we talk about the different filters. The calcium K, you're looking at the lower chromosphere. You get the magnetic fields, the supergranulation cells, and the sunspots. And then the hydrogen alpha, that's my favorite because it changes every single day. There's new filaments, prominences to look at. And with the Lunt 152, I love watching the spicules on the limb of the sun. It's like little flames, and it's very, very unique. And when I set that up for outreach, everyone comments about that as well. And this is the current view of the sun. So if I'm in hydrogen alpha, so if I'm looking to image the sun and I want to see if there's some nice prominences or what's going on, I'll go to the NSO Gong website. And the address is at the bottom of the screen here. And this is actually a live image of the current view of the sun from Mauna Loa, Hawaii. And you can see there's a prominence and there's a nice little filament. I don't see any sunspots on the disk, but because we're in solar minimum, I'm not really expecting to see that. And the white light filter, this is cheap, well, inexpensive and easy to build. And you can see on the left, I have the one I built myself with some solar film. And then on the right for my DSLR, I have the Daystar white light filter, which I ordered off their website for very cheap. And you can see the results that it will give. You can look at the sunspots very nicely, and you can see a lot of the granulation starting. And same thing with the Herschel Wedge. It just goes on your the diagonal, and you can attach a solar continuum filter in front if you wanted to break that down and to narrow the bandpass down. And this is the Bader solar continuum filter that I was talking about. Then it's 540 nanometers, and the bandpass is about 10 nanometers. And this is where you can really resolve the granulation cells, and it makes your white light image very, very nice. And it's almost comparable to a calcium K image, because when I'm imaging with the solar continuum filter, people will sometimes confuse it and think that it's a calcium K image. But I'm like, no, this is the white light filter with the wideband solar continuum filter. And then here's the calcium K that I use. It's just a diagonal that goes into the LUNT 152, and then I attach my camera to it. Very simple setup. And again, you just want to make sure when you're swapping out filters, put the cap on the scope just to ensure safety, and make sure that you're not burning yourself or the ground, or nobody walks by and looks up into the scope when the diagonal's off. Just a couple more calcium K images from the solar star party at NEAF, which was a blast. I always set up there in the courtyard. And then the hydrogen alpha filters, where we look at the outer chromosphere, and you'll see the filaments, prominences, and a lot of the spicules. And one question I get asked all the time, and every time I'm out doing outreach, everyone says, oh, I have a nighttime hydrogen alpha filter. Can I use that on my scope? And the answer is a big no. The hydrogen alpha filters are too wide of a bandpass. So when I'm using like the Astrodon 3 nanometer filters, which equals 30 angstroms, I'm imaging at about 0.5 of an angstrom, and which would be about 0.05 nanometers. So you can see how wide that is when you're out there with your hydrogen alpha dedicated solar scope. So do not use a hydrogen alpha night filter for solar imaging. That's too wide. You'll damage your camera, and if you're looking through it, you'll damage your eyes. And then when you're double stacking adds an extra echelon to the image train, so it narrows the bandpass down. So if you're using a LUNT 60 millimeter scope and you're at about 0.7 to 1.0 angstroms, you're bringing that down to about 0.5. So that you can see, you'll be able to see more detail on the sun, but the prominences aren't going to be as resolvable as a single stack scope would be. So that's why Daystar, for example, I'm sure everyone's heard the Daystar chromosphere version and the Daystar prominence version. And that's why there's a little bit, the prominence version is wider, so you're going to see more prominences. Whereas the quark chromosphere, you're going to see more detail. But you can always bump up the exposure to resolve the prominences and the details. So that's why if someone asks me, hey, should I get the Daystar chromosphere or the prominence, I always recommend the chromosphere version, because there's more you can do with it. And the LUNT 50, which is on the lower end of the LUNT scopes, it's a great scope. I was playing around with that at a barbecue, showing that to a bunch of kids. The only thing I didn't like about it was the helical focuser, but they actually have a feather touch focuser that will replace that. And it's a great small scope, and I have a lot of fun with it. They also make a double stack echelon for the front of the LUNT 50, and your starting price is $849 on that. The LUNT 60, and I threw the prices in because everyone asked me, hey, what's the price of this? What's the price of that? That way you can see the prices right there on your screen for you. And I did it with all these solar scopes that we'll go through with the different companies. And then the LUNT 60, you have a tilt tuned version or a pressure tuned. For imaging, I prefer the pressure tuned version just because I feel I have more control over the tuning, and the solar disc, it's easier to get a nice, nicely illuminated disc. Whereas the tilt tune, I feel that there's more of a sweet spot and it's tough to get that nice image. And the Daystar cork, which you can use with any, just about any refractor, you just want to make sure if you're using it over an 80mm refractor, you're using an energy rejection filter, such as like the Beta or UV-IR, or you can use a front-mounted DERF energy rejection filter, just to reject the harmful rays so it doesn't get to your camera or damage the Daystar cork or overheat the cork. And this is the UV-IR filter I use. And I use this safely with my LUNT 152. And I don't use it for long periods of time, just because 152mm is a lot of light going through. And I just worry about it overheating the cork. But I haven't had any issues with it yet. And I'm planning on getting a front-mounted energy rejection filter in the future for it. Just because if you're using the 2-inch Beta UV-IR filter screwed into your diagonal before the cork, you're getting a lot of thermals in the tube, whereas the front-mounted energy rejection filter will eliminate those turbulence in the inside the tube. So that's why I'm going to go with it. It's a little bit more pricier. Actually, it's a lot more expensive, but for imaging, I feel that it's going to improve my imaging down the road. And this is what I'm talking about, the front-mounted energy rejection filters. And one safety note on this, you do not want to use an energy rejection filter alone without a filter, like a hydrogen alpha filter or a calcium filter, because all it is just rejecting basically the UV-IR light, and you still have that high-powered solar energy coming through the tube at you. So you always have to make sure you're using a properly filtered scope with the energy rejection filter. And this is a new scope that Daystar came out with, and I actually had a great time with this. It's the Daystar Solar Scout, and it's probably one of the least expensive scopes on the market. It's at $695, and it's very narrow band pass at approximately 0.5 angstroms. And I could resolve the disc with my eyes, and you can see this image. This is just a quick, simple image on my front deck with the AVX mount. And I think it's a nice image comparable to the Coronado PST, which is around the same price. But then when you pay for the front mounted double stack, you're paying another $600. You're looking like $1,200 for that. And this is the Coronado PST, which I started out with. And it's a 1.0 angstrom, and it's a tilt tune scope. It's so easy to use. The hard part is to achieve focus with your camera. So what I did was I milled down my eyepiece barrel just to get that sensor a little bit closer to the focal point so I could focus on the sun. And if you ever have any questions or anything, my email's at the end of the presentation. Feel free to reach out to me. And I love and I can talk about solar imaging all day long. And these are some images with different scopes that are typical of seeing. So when I first started out, these are Coronado PST on the upper two. And then on the right is a LUNT 60, an inverted image, because I like the filaments. It gives kind of a three-dimensional look to it when you invert the image. And then the bottom two are Coronado PST. And then when you break out the LUNT 152 and the Daystar cork on the 152 scope, you really can see a lot more prominences and filaments and get that surface detail and the coronal loop. So I always check in once a day on that Solar Gong website just to see if there's any coronal loops, because I love to get out there and image those. So I just love the flow. And now that I have that solar guider, I can lock onto the sun and track it, and I can do a time-lapse image, which I'm going to start getting into on that. And here's a couple more hydrogen alpha images of the sun. And when you're imaging the sun at higher focal lengths, you have to be really careful with the seeing. I live in the Northeast where I have the jet stream over me constantly. So my planetary, if I want to get out there, image Jupiter, it's always garbage seeing. And same thing with the sun. The prime time for me to image is early morning between 9 and 11 a.m. or late afternoon about 3 to 4 p.m. If I'm imaging around noon, I notice my seeing is jumping around, and there's a lot more thermals, and the atmosphere is very unstable, and I don't get the excellent see. Well, not excellent, but I don't get the decent seeing that I do get in the morning. So my preferred time to image is in the morning. And again, the seeing's dependent on the atmosphere, the wind, the temperature, moisture in the air, and high level clouds. And there's going to be some high level clouds that you can't see in the sky. So I'm going to show you a couple apps that I checked to see if it's worth going out. The first one that I look at is the jet stream map. And you can see the jet stream is is south of me, looking at New York. So this would be a good day to go out there and image. And this is right on weatherstreet.com. It's under the jet stream map. And then I also look for the weather pressures systems. So I always like to image when there's a high pressure around because it's more stable air mass and it's nicer weather. And again, this is weatherstreet.com. You also have the clear sky charts, which you can look at cleardarksky.com to look up for your area. But my all-time favorite is Astrospheric. It's a new app, and it has everything. It has your clear sky, the dark blues. It also has your upper level clouds, the transparency. And also, if you're looking for the dew point, it'll give you a dew point map. It'll also give you satellite imagery and radar, and it'll give you the sunrise, sunset time. So you can plan your day accordingly, and you can look at the weather as well. So I always check that when I'm getting out there to do some outreach. And this, you can see, this is the seeing. This is a clip that I took, and you can see how the seeing jumps around and why it's important for your seeing to be steady and stable. And I'm going to show you a trick that I use with a solar scintillation monitor too. So if I'm out there, I can set my solar scintillation monitor to auto capture when the seeing is at the best, and it measures it. So this is the Airy Lab. They make a solar scintillation monitor. There's also a do-it-yourself solar scintillation monitor that you can make for, I think it's like $45. You can make it using a diode, and you can get a plug-in for fire capture to have it automatically capture the solar images when the seeing is at its best. And this is the solar scintillation monitor set up on the Lunt 152. And you can see it has an LCD display that will monitor the seeing, and it will also display the graph on the computer as well, and it will trigger the capture. When everybody asks me what imaging software I use to capture the image, when I'm using the ZWO EAF, which is the electronic autofocus, I use the ASI Cap app by ZWO. It's free image software. And I also used Janica Astro, which is made by Airy Lab, and they're the ones that developed the solar scintillation monitor. But I find myself mostly using fire capture, and it's also free to use. And I use that also during my outreach to broadcast a live image to the computer. And it works on MacBooks, Apple, and PC computers as well. And when I'm capturing my image, I'm looking at a solar disk feature that I'll focus on, and I'll capture about 2,000 images using the 16-bit mode selected and capturing it to a serial file. The serial file is going to be the best because it's not reducing your image or condensing it down. So it gives you more ability to process that file. I adjust the gain and the exposure, so the histogram is about 80 to 90%. I don't want the gain too high because I find the image starts to get pixelated. So I like to use the minimum gain I can with the exposure and controlling the exposure, so I'm not slowing my frame speed down too much. Because if you don't use enough gain and your exposure is too high, you're going to see your frame rate's going to drop quite a bit. And plus, if you're underexposed, you're going to lose detail. And if you're overexposed, you're going to lose detail, and you're not going to be able to get that back in processing. So I like to look at the histogram and make sure it's not cut off and it's not too short on that. And if I'm taking a image of a prominence, I'll take a longer exposure image and I'll bring out the details of the prominence. And then I'll merge that together with a shorter exposure and I'll work on the surface detail and combine them in Photoshop so I have both exposures, because you can't have both. You can't focus, or you can't control the exposure for the prominences because your surface detail is going to be blown out, and you can't have the prominences as visible with the surface detail how it is. So this is an example of fire capture on my MacBook. And you can see the histograms in the, I ideally like it in the upper third. And so you can see here it's about 2/3 of the way. And then this is also fire capture. And this is Janica Astro with a full disk image in hydrogen alpha. You can see a nice filament on the surface. And then this is ASI cap, and it's the, you can see it has the control of the electronic autofocuser on the screen. But all the software is about similar. You have the exposure control, gain control, and you have your histogram, and that's all I use. Some people like to control the gamma to bring out surface detail, but I don't like the gamma detail. I like to process that myself to bring out the detail. And the flat field corrections, sometimes if you image the sun, you'll notice you have some dust bunnies or some Newton's rings or uneven illumination, and slight defects in the image will really screw up your image. So I'm going to show you how to take care of that with flat fields. So you can see here, this is a raw image that I captured. You can see a couple dust bunnies on it. And then to flip that over, here's your flat field image. So this is the flat image. And how I do that is I just rack the focus in a little bit just to defocus the image. And you can see a couple Newton's rings on the right side. So I'll bring it back just to mirror it. So you can see the raw image with the surface detail. You can see the flat field. And now when I combine it, it cleans your image up. And this isn't processed. This is just with the flat frame applied. So you can see how it really cleans up your image, gets rid of the Newton's rings, and it brightens it up a little bit with the illumination. And here's an example of the Newton's rings. And you can see how it's a nasty pattern of ringing effect. And when I have people catch images with their cell phone, the cell phones are very prone to this because people don't hold their phones, and the Celestron XYZ isn't always flush. So you're going to get a little bit of Newton's rings. They make an adapter. ZWO has a nice Newton ring, a tilt adapter, and Daystar also has an interference eliminator, which is a very nice device as well to use to eliminate Newton's rings. And then when you stack the image, I like to use Auto Stacker for my stacking. I used to use Registax, but I use Auto Stacker and then I bring it to Registax. And the importance of using stacking is because the noise will decrease and the atmospheric disruption stabilizes when you stack a series of those images. There's also a common misconception that the resolution increases. The resolution always remains the same. And when I'm looking at my final stack of images, I'm only stacking about 20% of the best images. And I'll look at my graph and I'll increase or decrease it depending on how my images look, depending on the seeing. But average seeing, I'll only stack about 20% of the images, which is about 200 of my images if I'm using 2,000 frames. And this is the Auto Stacker screen. It's free stacking software. You can apply your master flat in there, and you can create your master flat on the screen. And you can see you go up to image calibration, create master frame, and then it will be applied. And then that's how I cancel out that. And by defocusing, you can't really do that for full disk images. And I didn't talk about this earlier in the presentation, but when I'm doing a full disk image, I'll use a vegetable bag from the grocery store, and I'll use 2 of those, and I'll just put them over the front just to distort it. and I try to mirror. I'll take a screenshot with my iPhone of the histogram, and I try to mirror that histogram with the exposure, so I can get a nice full disk that's distorted, and then I'll use that as my flat field for a full disk image. And then another thing you want to be sure that you do on the when you're going through your settings, you'll see under color, it's grayscale. If you're using a monochrome camera, be sure that's on grayscale, because there will be times where I don't check and I'm using a monochrome camera, but it's auto detect, and it will tell it to use the RGB format, and it will add a couple little color flaws to the final image. So you want to make sure that's on grayscale. Then you add your align points. For my alignment points, I like to use the auto align points in the grid, and I like to be around 674, 600 align points. So that's what I look for. It's not too big and it's not too small of an align point to align your image. And you just follow the steps. You'll see on the up, after you analyze your image, you're going to get the quality graph, and that's where I can see the quality of the images and what it looks like. And then you can see where I did 20% of my frames to stack. And then step 3, which is the final after you add your line points, is to stack it. And then here's the difference there with stacked. And then once I have it stacked, auto stacker, you can have it sharpen your image automatically for it, but I like to control it myself. So I bring the raw image right into Registax. And then when you load it, you don't want to stretch the intensity levels. And then you'll get your raw image, and then you adjust the wavelets to custom to sharpen it up a bit. And you can see I like to bring one up quite a bit, and I'll also sharpen it. You can see on the tabs above the layers, there's denoise and there's sharpen. So I'll bring up for layer 1, I'll denoise it. I'll bring it up to 0.20. And I'll leave that as it is. And the bottom one I'll bring up to 0.10. But all this is experimentation and seeing what works for me. So this is what works for me. And you're more than welcome to copy this down and see how it works with your setup. And then in post-processing, you have GIMP, which is free, or Photoshop, which costs money. I use Photoshop. It's worth the money. And I like to be able to apply my solar transits very easy in Photoshop, and you can adjust the brightness, the contrast, levels, exposure, and the final sharpness. The final step, if you're using a monochrome image, is to apply the false color to it. And I like to be scientific with my images and try to match up the color. So if I'm doing a calcium K image, I like that deep purplish image, as opposed to the yellow, which everyone expects the sun to be. However, if I did a solar image of the eclipse, I did a yellow image, which everyone went crazy over, and then the purple one, people were criticizing too much. So sometimes I will customize it and put that as a more yellow image. And this is, you can see how I apply the color, and then the final image. Other helpful software. So if you're using a mount that isn't properly polar aligned, there's a PIP, Planetary Image Preprocessor. This also works good for planetary imaging, Jupiter, Mars, Saturn. It will stabilize your image. So if you have Jupiter drifting off the screen, or if you have the sun drifting off the screen, this will stabilize your image better. There's also IMPGG, Image Post Processor, which also is a great way to process your solar images. And for upcoming solar transits, including like the International Space Station, and to keep up to date on those, there's calsky.com. You can sign up for alerts, and you can be alerted to lunar transits and solar transits on there. And for more information, Stephen Ramsden has a great page, solarastronomy.org. He also runs Sunlit Earth, and there's a solar chat forum. And the solar chat forum is very, if you have questions, there's awesome people on there that answer them, and they like to modify scopes and tinker around. And then there's a solar activity group on Facebook, which is one of my favorite groups on Facebook. I check it every day and look at everyone's posts, and I like to see the newcomers on there and see their images. And I stay up to date. And if it's cloudy out my house, even though I'm looking at the solar gong, I always go to solar activity, and there's somebody around the world that's taking some great images. And that's run by John and Pam, and John O'Neill and Pam Chivak. They do a great job on that page as well. So here's my email address. If you guys have any questions or want to reach out to me about solar imaging, I love to talk about it. The best way to reach me, though, is on Facebook or Instagram. Facebook, I'm very active on. My email, I'm active on my email, but I'm bad to get back to people on there just because I have over 20,000 emails and I'm horrible with checking my email. But Facebook, it's an alert right to my phone, so I'll be able to respond quickly. And I also have a Facebook.com, a Facebook page where I post my images to. Connolly Astronomy is what is that. And I also have a 4-year-old son that loves to get out there with me in solar image. I got him an ETX 90 scope, and I put a little white light filter on it for him, so we image and play around with the sun scopes together out there. So we have a great time with that. So that's the conclusion of this. I know I can talk, but I cannot hear. So I believe Alex is going to relay stuff
I'm
back
on the
to
phone
me.
with you now. Can you just take it off speakerphone and put the phone to your ear?
Yep, I got that. So I got you.
Okay. Now, do you still have your speakerphone on?
And nope, I don't have speakerphone on. It's just
Okay.
up to my.
Okay, I've got a problem in that I'm listening to you both live and on my phone, and it's confusing me. So give me a break here. I am going to ask you a question. Tolga is going to look at. Tolga is going to look at what's on the question list, and he's going to develop whatever questions we're going to have.
Okay.
And I am going to ask you a question or two of my own while Tolga is doing that.
Okay.
What special issues come up? Oh, by the way, people have said it over here on the YouTube comments and stuff like that. They really like the presentation. The real tour de force, the equipment and all that good stuff. So really, congratulations. What do you have to watch for, particularly with the transit? You have a plan for what you're going to do that morning?
Yep. So I practice over and over, and my ideal setup is my Lund 80 millimeter with the calcium K filter. I don't like to image transits in hydrogen alpha. It's doable and possible, but I think the calcium K image brings out the transit the best. Obviously, white light filters will do a great job bringing out the transit, but at the same time, you don't have the detail of the sun. I mean, you'll get some granulation, and if you have a sunspot on the sun, you'll get that. But I like the calcium K because you get a lot of the detail, the solar disk detail, to go along with the transit, the Mercury transit.
Okay, so you're going to set up that morning and get all ready to go. Tell me about the black drop. Is that the name of that thing? The black drop is that when the planet just hits the edge of the sun and you can't quite tell what's happening.
Yep. So that's the first contact. So that I had the time right here. Let me just bring that up. Yeah, so you want to get that. Let me just go to, I'll tell you exactly what time that is.
Don't forget to share your screen.
Here you go. Oh, is it sharing? Do you have the screen share on there?
No, you're not sharing your screen right now. Just go up in the upper left there, and the green, white arrow on the green arrow.
Okay.
I remember you had to be in the hangout itself.
Yeah. Do you still have me on the screen?
Yes, we're seeing you live.
Okay, I'm gonna keep going on this then because it says Google Chrome not responding. So I'll keep going on that.
Yeah, just
So the first contact when you have the black dot, when you have Mercury coming on, it's going to be about 12:35 UTC time, so 7:35 a.m. my time. So I'm going to be out there set up well in advance. So I'm going to try to be out there at probably around 6 a.m. To do that. And then you have the greatest when Mercury is going to be in the center of the solar disk. You're going to have that at 10:19 a.m. Eastern time or 15:19 UTC time. And then the end of the transit, when you have it leaving the disk of the sun, is 18:04 UTC time or 1:04 p.m. Eastern time.
Okay. Have you given any thought to making a movie of the transit?
I'm sorry, making a what? Movie of the transit?
Yeah, a video of the transit. You know, you
Yep.
take a
So I've done that actually. I have done that with the ISS transits where I'll condense all the images into a movie and I'll speed it up, slow it down, and then I'll combine them all. So I have the images I'll have a series of images showing the transit going across the disk of the sun. So that's what I plan on doing as well for the Mercury transit.
Okay. Tolga, how are we on getting arrangements with the rest of the questions?
So I don't see any questions on YouTube. There were a lot of talks back and forth, but I have a question if you can relay that to Tim.
Okay.
On his, he talked about a Lunt 152 telescope with a Daystar quirk.
Okay, hang on. You talked about a Lunt 152 telescope with the Daystar quark on top. Okay.
Yes.
I just wanted to clarify
solar
that.
scope, and then the Daystar was stuck on top, or what?
Yes. So yep. So I use the nice thing about the Lunt 152 is that I can take out the hydrogen alpha filters. So I can use it as a 152 achromat scope, or I can use it with the hydrogen alpha echelon, and it kind of narrows the bandpass down and brings out more surface details. So you can use it either or on that setup. And you can see behind me, I have the Lunt 152 double stack setup, and I also have the Lunt 152 with the calcium K above it. And then over to the left, I have the Lunt 60 millimeter double stacked, and then the Lunt 80 millimeter, my Lunt engineering that I use with the calcium K module by Lunt.
Okay. Tolga was also asking, Tolga, did we answer your question sufficiently?
Yes, that was answered. I just posted a new question over here.
Yeah, I see.
What's your go-to solar
Got it. I see it's typed in.
for outreaches?
When you go to a solar system for outreach, what do you take with you? What's your
So depending on the weather, so we just had an event last weekend at my local observatory, and it was scattered thunderstorms. So I brought my Lunt 60 with my Lunt 80. My Lunt 80 is always my go-to scope, and that I'll always have a calcium K filter on it, and I'll be running a live feed to my MacBook computer with fire capture. And depending on the weather, it'll either be my Lunt 60 double stacked or the Lunt 152. And the Lunt 152 for big events, I'll always have the Lunt 152 on the Celestron CGEM DX mount and the Lunt 80 millimeter side by side. So my choice of instruments for solar outreach and solar imaging is the Lunt 152 side by side with the Lunt 80.
Okay. Tolga, any other questions popping up? There's extensive discussion over there. That's what we're here for. We're here to be kind of a sounding board.
Yeah, there's extensive discussion, but I haven't seen any direct questions.
Yeah. Okay. Tolga says there hasn't been very many direct questions about your presentation, but you have given us your email there at the end of the presentation. And
Mhm.
I want to remind everybody that you can't set up on November 11th and get up at 4 o'clock in the morning and review everything Tim has just told you. Go out and take these pictures of Mercury crossing in front of the sun. You got to start tomorrow and the next day and the next day practicing this solar imaging stuff. Also, you need maybe to go back. Tim gave us a few minutes on image processing with stacks and so forth. Tom Bash, remember, a while back gave us a rather extensive presentation using the moon, but much of the stuff you do for the moon, you also do for solar high resolution processing. So you can get a lot of that stuff from Tom's presentation by going through the YouTube videos that are already stored up, and you will find them in the past shows section of our website. With that in mind, unless we've got other questions, we want to thank you all for sticking with us. I should tell you that as far as the Astro Imaging channel goes, we do appreciate your donations to help keep us going and stuff like that. We've got to pay for the website. We do appreciate you subscribing especially, but most of all, we appreciate you coming here and participating in workshops, in the discussion on YouTube, and those kinds of things. We are a community of we're just folks. I mean, you could see when we finally got the system for tonight working, you could see how happy we were at the very beginning of this show that we were all just so surprised that we had actually gotten this thing to work and go live. I should tell you that as we started the program, there was a little message from YouTube saying, by the way, the streaming that we're using is going to die on August 1st. So we don't know what exactly is going to happen next Sunday. We will continue to work on it, and we are going to do our best to become technically proficient at what we're doing. If there's anybody out there who's a YouTube genius, would like to help us, please get in touch with us. Okay, we would love to have you here. We would love to take the advice. Okay, with that,
If you're going to say that, we might as well say what the problem is. The problem is broadcasting a chat room. We can have one person do a broadcast. You know, that's not a problem. That's every YouTuber does that. You go and there's a single camera and single person talking. The issue comes in broadcasting a chat room of 5, 6, 10 people talking to each other. Currently, Hangouts is directly integrated with YouTube website. They're taking that away. So we need to come up with a method to broadcast an X. We could use Skype. We could use Zoom. Some sort of a chat software. We need to broadcast.
Yeah, I can hear you. I can hear you, but I can't hear the broadcast.
So that's all. I just wanted to say that. That's it.
okay. It's about time for us to go for the night. Hang in there, everybody. We will see you one way or another next week. We will figure out how to do it, okay? And we're going to stop the broadcast. Tim, stay on the line here, and the rest of you guys know to stay on the line. So good night, everybody, from the Astro Imaging channel.
Good night, everybody.
Bye-bye.